Good morning and welcome to the third lecture of Measurement and Engineering. Last week we've been talking about thermocouples, about temperature sensors, and the last thing I showed you is the manufacturing of thermocouples. So thermocouples are just one of the contact sensors for temperature that we will discuss, and they are manufactured by welding. Just to repeat briefly the basic terminology for thermocouples. Thermocouples are made from dissimilar metals in our case, and the welded end is here. It's called hot end or hot junction, and at the other end we have the cold junction, and this is where we measure, where we get the reference temperature. To remind you that thermocouple does not measure temperature directly, but thermocouple measures temperature difference. So if you want to measure temperature T1 at the hot junction, you need to know also T2, and the voltage that you get on the thermocouple output is proportional to the temperature difference. Thermocouples are letter coded, so the type of thermocouple is encoded in the letter that you will find in the description. So for example, thermocouple type J, the metals in the thermocouple are iron and constantan. Constantan is an alloy of copper and nickel. It has special properties also in terms of thermal expansion or electrical coefficient of resistivity, thermal coefficient of resistivity. So we use this metal and the welded end forms the measuring junction in a thermocouple type J. Thermocouple type J is one of the most common thermocouple types. The other very common type is also thermocouple type K. So those two you will find in our labs, and those are probably the most common ones that you will find in industrial applications. Type K is composed from nickel and chromium, that's one part of the thermocouple, and nickel and aluminium, that's the other metal. In both cases, the voltage that you get on the thermocouple output is very, very small. It's in several tenths of microvolts per centigrade of the temperature difference. Obviously, the sensitivity depends on the composition. So for thermocouple type J, we have sensitivity roughly of 53 microvolts per centigrade. For thermocouple type K, it's a little bit less, roughly 41 microvolts per centigrade of temperature difference. This value, however, is not constant, and thermocouples in a wider range are not linear. So the values that you have here, so the 52.7 and 40.96, are valid only within the range of 0 to 100 centigrades. In other ranges, you can use thermocouples as well, but the sensitivity will be different. We will see that in a few minutes when I will show you some steady-state characteristics of thermocouples. So keep this in mind, that it's a very small voltage. We need to amplify it, and the amplifier needs to be very close in the close vicinity of the thermocouple itself, and that it's not linear in a bigger range. Thermocouples are also color-coded. So just by looking on the coating on the thermocouple, you can tell what type that is. Here, just for information, you have many thermocouple types. This is the American standard, and this is the international standard. So luckily, the most common one, thermocouple type J, you see it has a black color. So, for example, the thermocouples that you will use, or you probably already have used in the lab, are thermocouple type Js. So here I have an example of thermocouple type J, thermocouple wire. You see it has a black color, and it's thermocouple type J. The individual wires in the thermocouple pair are also color-coded. So here for type J, you see the positive wire is black, the negative wire is white. Here in the US standard, it's different. But since the voltage has polarity, we need to be able to distinguish also the polarity of the voltage. Because if the temperature difference will be negative, the voltage will be negative as well. So you need to connect the positive wire to the positive terminal on the measuring instrument and the negative wire to the negative wire. Here, I'm not sure if you can read that, but here you have data about the maximal range where the thermocouple of a specific type could be used. So thermocouple type J, they say maximum 1200 centigrades, but this is the very maximum temperature. Typically, this kind of thermocouple is used for much lower temperature. And by much lower, I mean something around 800 centigrade, 750, something in this range. The maximum temperature depends not only on the thermocouple type, but it depends also on the insulation material. So the thermocouple wires that you have here as examples are obviously good for lower temperatures since the insulation material is plastic. If you want to use thermocouples for higher temperature ranges, you need different insulation materials. And for example, this is a thermocouple with ceramic insulation. So you see basically thermocouple wire encased in ceramic tubes, and this can be used to much higher temperatures. This is also thermocouple type J. In the table, you can also read what is the environment where the thermocouple wire can be used as a bare wire. Here for thermocouple type J, you can read that it can be used in reducing vacuum, inner atmosphere, but that it has a limited use in oxidizing atmosphere at high temperatures. That's because the metals will oxidize in this kind of environment. Different thermocouples will be good for different applications. So for example, thermocouple type K, you see it has a different temperature range, up to 1372 centigrades. But again, this range is really the maximum that you could use. But in reality, the real temperature ranges are much lower. And here you can see the applications. It can be used in clear oxidizing atmosphere and inner atmosphere, but on the other hand, limited use in vacuum or reducing atmosphere. So this is completely the opposite if you compare that to the thermocouple type J. The other thermocouple types are not that commonly used, but you may need to use them for specific applications. For example, if you want to reach higher temperature ranges. For example, this thermocouple type R or type S, you see the composition, platinum, and the other metal is either an alloy of platinum and rhodium with 13% of rhodium or 10% of rhodium. And you can see that the temperature range is much higher. Since this thermocouple will use platinum, it will be obviously much more expensive than the iron in thermocouple type J. So this is used for high temperature applications. And if the distance between the hot junction and cold junction will be very long, you will have to use the compensating wires instead of the thermocouple wire directly, because it would be very expensive. I have here some examples of the thermocouple wires, thermocouple pairs. So in here, this is a selection of different thermocouple wires. I'll pass it to you in a moment. You will see different diameters. here and the different types of shielding. So some thermocouple wires are just encased in a ceramic pipe like this for higher temperatures. Some are encased in a complete metallic protective layer, and this will allow you to connect them also in high temperature applications. Here I have a different thermocouple wire. This is type T. This is type N. Here, that's this one, the pink one. And this is for a little bit higher temperatures than the plastic encasing, but still lower than the ceramic layers on top of that. So take a look on the thermocouples. How to read the values from a thermocouple table. So this is an example of a thermocouple table. You will use a similar one just for type J on the labs, or one group already has used that. Here we have voltage in millivolts. So the voltage is very small. And here we have temperatures. This is in centigrade. So for example, if I would be looking for temperature difference of 250 centigrades, then I have 250 and this would be here, 250 and 0. If I would look for 297, then it would be 290 and 7, so it will be 12.084 millivolts. So this is how you use a table. If you want to use the negative ranges, then for example minus 195, then you have minus 190, and this is the minus 5, so it will be minus 5.813 millivolts. So you see that when the temperature is negative compared to the reference junction, then we will have a negative voltage. In all cases, in the whole range that you see here, that the voltage that you have is very, very small. So it will be very sensitive to electromagnetic interference. You typically need to filter out the interference from the power network, so 50 or 60 hertz. And you need to make more samples, and you need to calculate the averages and have an amplifier installed very near this hot junction. This is a chart that shows you that the steady state characteristic of a thermocouple is nonlinear in a wider range. So for low temperatures, you see here, for example, thermocouple type K, that's this line. Here you see that the thermoelectric voltage is nonlinear. If you work in smaller temperature ranges, so let's say somewhere like minus 30, minus 50 centigrades, then this part can be approximated with a line, but in the larger range is definitely not linear. The same is true also for high temperature ranges, high temperature thermocouples. So for example, type J, see, looks like a very good line. So then it depends on the degree of accuracy that you want, if it's linear or not. For example, thermocouple type C, you see, gives you larger range, up to 2,300 centigrades. But at the end, it's becoming a little bit nonlinear. So we have to tell that the thermocouples are nonlinear in the whole range. However, if we operate with small temperature ranges, such as, for example, 100 centigrades, then we can say that it's linear with a good degree of accuracy. Thermocouples can be either used directly in your application, so you have the hot junction directly in your medium or in water or in the air. But typically we need to protect the thermocouple from mechanical and chemical damage. So the information in the table about the clean oxidizing and reducing atmosphere and so forth was for the bare thermocouple. So if you would take the thermocouple wire, for example, I would take a thermocouple like this. I would place that directly in the application, and the hot junction would not be protected at all from the contact with the liquid. In industrial applications, we typically need to provide a really better degree of protection. So the thermocouples are hidden inside the thermal well. So we have discussed thermal wells last week. Thermal wells are basically just a pipe that is closed at the end, and the thermocouple is inside of the thermal well. There are three ways how the thermocouple itself can be connected or not to the thermal well itself. We'll discuss that on the next slide. Here I'd like to show you some examples of thermal wells for thermocouples. So it looks like this. From the outside, you can't really tell if it's a thermocouple or if it's a different kind of sensor. You have to look on the specification that are written on the thermal well. So here I have some examples of thermocouples in a thermal well. So this is a thermal well, a ceramic one, with a thermocouple made from platinum and platinum rhodium inside. So this would be type R or S, and it says up to 1600 centigrades. That's due to the ceramic thermal well. If it would be a metallic thermal well, such as this one, this is a type J thermocouple, then this is good for 800 centigrades. Thermocouple thermal wells can look in a different way. So this is also a type J thermocouple thermal well, but here they say it's only up to 600 centigrades. So take a look on this, so that you have an idea how a thermal well looks like. It's all written on the nameplate what type that is. The dynamic response of a thermocouple obviously will depend also on the thermal well. The better mechanical and chemical protection the thermal well provides, then typically the worse the time constant, the longer the time constant. Because if we want to have better mechanical protection, we add more material, and therefore the heat transfer will be worst. So the thermocouple time constant will also depend on the properties of the thermal well. The thermocouple time constant also depends on the diameter or cross-section of the thermal well itself. So here, to give you an idea about bare wire thermocouples, here is a transient response from different thermocouples. You see here we have time in seconds and output voltage from the thermocouple, and those are different diameters. So in this direction, the thermocouple wire diameter is increasing. So here you have a bigger wire diameter, and this is a smaller wire diameter. So smaller wire diameter means that it will heat up faster, and that it will have a smaller time constant. There is, however, also a trade-off between the maximum temperature range of the thermocouple and the wire diameter. The maximum temperature range goes in exactly the opposite direction. So the smaller the wire diameter, the smaller the temperature, the maximum temperature where you can use the thermocouple. So there is a trade-off between the wire diameter, insulation, cost, time constant, and so forth. Here you have an example how we can install the thermocouples in the application. So either we use a bare wire, we install the thermocouple directly inside the application, and the hot junction is directly in contact with our liquid or with our gas that we want to measure. Obviously, this has the advantage that this bare wire has a very fast response. The heat transfer is very fast, and there is no material between the environment and between the hot junction itself. So this bare wire installation will have a very short time constant, and this will be one of the fastest sensors that you can get if you want to measure really quickly. On the other hand, since this is exposed directly to the medium where you use it, this will have limited use only to dry areas, only to non-corrosive liquids and pressureless applications. So this is the best option if you have something like air and you want to measure for a short time, and you know that there will be no corrosion in your application and it's really dry. But it's the worst option if you know that this will be some corrosive application. If you want to protect the thermocouple hot junction, you can install that in a thermal well. So this is a thermal well installation. The junction in this case is insulated from the thermal well itself, I mean electrically insulated. So there is no electrical contact between the thermocouple wire and between the thermal well. Obviously this works only if the thermal well is from metal. So this material is an insulation material that electrically insulates the thermocouple. It should have a good thermal conductivity, but typically materials that have a good thermal conductivity, they also have a good electrical conductivity. So this insulates quite well the thermocouple. We add corrosion resistance, but this will have a longer time constant. So this will be definitely slower than the bare junction connection. So the time constant can be much higher. Here it depends on the thermal well, but to give you an idea, if I would take a wire, a bare wire like this, and use it and measure the time constant, this would have a time constant of, let's say, 1 second. So it will be very fast. If I put it in a thermal well, for example, like this big, it could easily have a time constant of 2-3 minutes. So it protects quite well the thermocouple, but decreases the sampling rate that you can get from the sensor. Somewhere in between is this third option. This is called a ground junction, and somewhere in between means that it has good corrosion protection, since it is protected by the thermal well. It has a faster response because the thermocouple is directly welded into the end of the thermal well. So it has a good heat transfer, so it will have shorter time constant than the insulated connection, but definitely longer than the bare wire. But on the other hand, since this is a metallic sheet, it will act as an antenna, and you can have problems with electromagnetic interference. So it really depends on the application whether you choose those three options. But if you want the measurement to be really fast, then choose this if it's non-corrosive. If you want good protection, then choose this, but it will be slow. If you don't have problems with electromagnetic interference, then choose this. It will be faster and still good protected. Here I have some thermocouple probes. So the thermocouple probes that you can find for handheld measurement instruments, they typically look like this. Those are contact probes. So the thermocouple is at the end here, and this connector goes into the measurement instrument, and you hold that against your object and you measure the contact temperature. Those probes, for example, are used also for handheld instruments, but you may find them also in kitchens where you want to measure temperature of the meat that you're cooking. So this is the thermocouple, and this goes to some thermometer. Here, a similar thing, thermocouple wire wound as a spring, and the thermocouple wire itself ends here at the hot junction. So then those are the standard terminals for thermocouples. I have here some probes that I'd like to show you. Here, this is a thermocouple probe type J, so iron cobalt. You see, it doesn't have the connector at the end. I have here a thermocouple wire. This is type T, so this is copper and constantan wire. And let me check if I have some more thermocouples here. Well, yes, this is also a thermocouple in a thermowell. It's quite massive from iron, so will protect it quite well, but will have a smaller temperature range than the ceramic one. Okay, we have seen that when we use thermocouples, we have the following problem. The thermoelectric voltage is proportional to temperature difference. So if I have the hot junction and cold junction, then the voltage is proportional to the difference between those two temperatures. And therefore, we also need to know the temperature at the reference junction. If we don't know that, we are able to read just the temperature difference, but not the absolute temperature. There are two ways how to handle this. Either you measure the temperature at the cold junction with some other kind of thermometer, like, for example, a resistive temperature detector, which we will discuss in a few minutes, or you have this cold junction on a constant temperature. So this is the way that I show here. This is without any compensation for the cold junction. So we have the measuring junction and we have the cold junction. So this is connected directly to the meter, and the thermocouple is giving me a voltage proportional to the temperature difference between those two ends. If for some reason the temperature around this meter will change, then I will change the temperature difference, and I will not be able to tell if it's this temperature that is changing or if it's that temperature that is changing. So we can use a thermostat. We can put the cold junction in, for example, in an ice bath that will be maintained at 0 centigrades until all the ice melts. And here we know that we have a constant temperature at the reference junction. So this will give you 0 centigrades, and here you will read the voltage. Other way would be, for example, to have this as an oil bath and heat it to, let's say, 50 centigrades with a feedback control. So this would be also maintained on a constant temperature, and since we know the temperature, we can easily read the absolute temperature at the measuring junction. There are another ways that are electrical ways, for example, like cold junction compensator, but we will not go into this. But so remember that for a thermocouple, we absolutely need to do this. The advantage of thermocouples is that if we already have an ice bath like this, we may use it for many cold junctions. So we can easily put 50 or 100 thermocouple junctions into the same ice bath, and here this will be a single and simple thermocouple wire connected where we want to measure the temperature, and this will give us a very let's say cost-efficient application. So thermocouples are easily manufactured, and you can use them in applications where you need to measure on multiple points. On the other hand, they are not the most precise temperature sensors. So it's good if you want to measure on multiple spots with an accuracy of, let's say, plus minus 1 centigrade. But if you want to measure something more accurate, then you need different kind of sensor. Some questions so far? Okay, so let me go to another kind of temperature sensors, and this will be called RTDs. RTD stands for Resistance Temperature Detector, and RTDs are one of the most common temperature sensors that you can find in almost all applications. The principle is that electrical resistance is changing with temperature. So if we know this dependence, if we know how the electrical resistance is changing with temperature, we can measure the electrical resistance and we can use it as a temperature sensor. Typically, the resistance depends on the temperature by this equation. So here you have an initial temperature R0. This is the resistance for 0 centigrade, and here T is temperature and alpha is the temperature coefficient of resistance. It's defined like this. So it's basically the difference between the electrical resistance for 0 centigrade and for 100 centigrade. So this is exactly what you see here in this equation. This equation in this simple form, however, can be used typically only in small temperature ranges, something like plus minus 100 centigrade. The reason is that this dependence is in general nonlinear, and only if we are within some small temperature range, and we can say with a good degree of accuracy that this dependence is linear. So for higher temperature ranges or for higher accuracies, you typically need to use a more complicated equation, something like in this one. Here you see it has the same philosophy. Here we have R0, we have A, that's the temperature coefficient of resistance, but we also have different coefficients for higher temperatures, so T squared, T cube, and so forth. It may be even more complicated, as you will see in a few minutes. So this simple equation that we typically use is only for a specific small temperature range, but since we will be always in our labs in this range, we will use this equation. But keep in mind that in general it is nonlinear. The metals for RTDs are the following ones. The first and the most common one is platinum. So all industrial sensors that need to measure very accurately are made from platinum. Here the second column is the temperature coefficient of resistance, and the third column is to give you an idea about resistivity. So the resistance of a given length of wire and with a given cross section. So platinum is the most common one for almost all applications. Nickel is used for applications that require less accuracy, or that can work with lower accuracy. We'll see it will have many disadvantages as well. On the other hand, if you look on the temperature coefficient of resistance and compare platinum and nickel, you will see that it has about double the temperature coefficient of resistance. This is nothing else than sensitivity. So in other words, how much is the resistance changing for a specific change of temperature? So in other words, if I would compare same sensors from platinum and nickel for the same temperature, then the nickel sensor would give me the signal that is twice as big. so it will be easier to read out, but as we will see soon, it will have also many disadvantages. The third one is copper. Copper is a very common metal. You see it has almost the same sensitivity as platinum, so the signal will be roughly the same. But on the other hand, if you compare the resistivity, then you see that there is approximately 1 order of magnitude difference between resistivity of copper and platinum. So copper has a very good electrical conductivity. It means that if you would like to produce a copper sensor with the same initial resistance, R0, as from platinum, the wire would need to be 10 times as long. So the sensor will be roughly 10 times larger. And we will see that it will have consequences on the resistance that we are using for the copper and platinum sensors. We'll start with platinum. Here you have an image how platinum looks like. Platinum is a very stable metal, so sensors from platinum will be very good in time. So it means that they will not change its properties in time. It's an inert metal, so it will be very stable. Platinum has a relatively high resistance, about 10 times higher than copper. So the wire can have large resistance. This will mean that we can use small current that will go through the sensor, since from Ohm's law we know that voltage is resistance times current, and if we read voltage, the voltage will be relatively large. So that's one advantage, that platinum sensors can work with a relatively small current that is going through the sensor. Platinum, since that's a very stable metal and it can be manufactured with a high degree of purity, then the result is that the sensors can be interchanged in the application without recalibration. So you just buy the sensor, you install that in the application, and if it's, for example, PT100 from one manufacturer and you had the same PT100 from a different manufacturer, they will have the same steady state characteristic. So you don't need to do any calibration, you don't need to measure yourself the steady state characteristic, you just exchange that and that's it. Platinum sensors are denoted like that. For example, PT100. PT stands for platinum, 100 stands for the resistance of the sensor when it's on temperature of precisely 0 centigrades. So a PT100 sensor has exactly 100 ohms for 0 centigrades. The PT100 is the most common sensor that you can find in industrial applications. You can also find a PT1000, which obviously has 1000 ohms for 0 centigrades, but this is a little bit less common than the PT100. Platinum, if you want to use it in a higher temperature range, is nonlinear. So if we measure the steady state characteristic of this sensor, then it will look something like this. You don't need to remember those equations or those coefficients. Just remember that it's nonlinear. From the chart, it may not look like nonlinear, maybe just a little bit, but from the equation we can see that it's nonlinear. This equation is for a larger temperature range where the PT100 can operate. Typically, the PT100 can operate up to 600 or 800 centigrades. And in the negative temperature, it can be easily 200, 270 centigrades minus. So those coefficients are valid for the higher temperature ranges. If we are within plus minus 100 centigrades, then you can easily use just this A coefficient. This is the sensitivity, so 3.9 times 10 to minus 3. And you can see that the other coefficients are roughly 5 orders of magnitude smaller. So if you would use that for small temperatures near zero, then this number and this number would be very, very small. But if you use that for example, 500 centigrades, then you have 500, well, this is in Kelvin, but so let's say 700 Kelvin here squared times this number. So this can already have and will already have an effect on the linearity of the sensor. Since platinum sensors are very stable and very, very accurate, the PT100 is the standard sensor that is used to calibrate also our other sensors. So in the international temperature scale, there are some defined points where you can fix that your temperature is really the one that you measure, and in almost the entire range from roughly 250 negative centigrades up to, let's say, 600 centigrades, the PT100 sensor is the one that is used to calibrate all other types of sensors. The sensitivity of a PT100 is 0.39 ohms per centigrade. So we now know that it has 100 centigrades, 100 ohms for 0 centigrades, and that the resistance is the resistance change is relatively small. We need to distinguish, for example, if it would be 1 centigrade, then it would be 100.39 ohms. So we will need some connections that are able to distinguish small changes of electrical resistance. And we will talk about that today at the end. Platinum sensors are manufactured in two tolerance classes, Class A and Class B. The difference is in the accuracy. So here you have Class A, and this gives you an idea about the accuracy. Class B is roughly 2 times less accurate than Class A. In this table, you can see how much this gives you in centigrades. So here, for example, Class A, let's say 0 centigrade, can be measured with plus minus 0.15 centigrades. So that's quite accurate. Obviously, when the temperature is increasing, then this tolerance will increase as well. But still, for 600 centigrades, which is the typical maximum range of a PT100, then with a Class A sensor, we can measure that within plus minus 1.3 centigrades. So it's really an accurate sensor. The Class B sensor typically twice as inaccurate as Class A. So for 0, you see 0.3. For 600, this is even worse, 3.3. But still, it is quite accurate. For example, compared to a thermocouple, I would expect this is, if you compare 600 and 3.3, this is something like 0.5%. So this is really accurate. For a thermocouple, typically you can expect something like 1, maybe 2%, maybe even bigger. So this is really an accurate sensor. Unfortunately, the tolerance classes and the degree of purity of platinum are different if you follow the European and US standards. So you need to be very careful which standard you choose. This is not to say that one standard is better and the other is not. This is just saying that if you have your application calibrated for a specific PT100 from one standard, and you replace that for some reason with another one, then you may have problems in accuracy. In this chart, you see the difference in degrees between the European and the US standard. So for 0 centigrade, they all have 100 ohms precisely. So the difference, the error that you make is 0. So this is, here it's fine. But for example, if you look on 600, then the difference is roughly 13 centigrades. So in the previous table, we've seen that 600 in a class A sensor, I can measure within 1.3 centigrades. But just by using the standard that's not adapted to my application, I can add an additional error of up to 13 centigrades, which is roughly 10 times larger. So be very careful about this. Use preferably one standard that fits into your application, and if you need to reorder that, specify the same standard. How does a PT100 look like? We will discuss 3 options from the point of view of construction of the sensor. And we will start with the glass PT100. A glass PT100 is made from a platinum wire. So this is a platinum wire that is wound in a coil. So this is a very thin platinum wire. The diameter is something around 0.05 millimeters, so 50 micrometers roughly. And this platinum wire is encased in a glass encasing. So it's a glass tube, and the glass, when it's melted, encases all the wire completely. So the wire cannot move freely in the glass. It's completely encased. The coil here, you see it's wound in a special way. It's called bifiller winding. And the principle is that the wire goes all the way very closely to the wire that is going back. So you see that from one terminal here, the wire goes like this. From second terminal, the wire goes like that, and continues all the way to the end. The reason for this winding type is that this limits the inductivity of this sensor. So if you wound a coil in this way, it will have smaller inductance than if you would start at one end, wrap it as a coil, and then go back. So the reasons here are electrical reasons. If we have smaller inductivity, then we can easily measure the change of resistance, and the changes of inductivity will not disturb the measurements. The glass PT100 can be used to temperatures typically up to 600 centigrades. That's the limitation of the glass. And you see the price here. The sensor itself is somewhere between 50 and 100 euros per piece. Here you have some pictures of the glass PT100s. I have here some sensors to show you. So let me see that. So this is a PT100, the glass one. You will see that it's very thin wire within a glass encasing. And this is a PT100 in a thermal well. So it's again protected. This is the internal thermal well that is then hidden in a bigger thermal well. The second version that we will discuss is the ceramic one. I forgot this image. For all PT100s, we will need a thermal well to provide protection. So The sensor itself can look like this, can be very small, can be bigger. The resistance is still the same, but it needs to be installed in a thermal well. So here I have some examples of thermal wells for PT100. So those are PT100s. See minus 52 400 centigrade, a small thermal well, not a really good mechanical protection compared to the bigger ones, but definitely faster and smaller time constant. Okay, and the ceramic PT100. From the outside, it looks almost the same, with the exception of the ceramic material. So it is also a platinum wire with roughly the same diameter, so roughly 50 micrometers. But it is placed into a ceramic tube with two holes that are looking like this. So this is the ceramic pipe. Those are the two wires, and it goes from one terminal and back to the other terminal. Here it's not done in the biffill winding because it's not encased in the ceramic and fused inside, but the ceramic wire is allowed to move freely inside this opening, inside this hole. The reason for this is that if the materials that have different thermal coefficients of expansions, then if you change temperature, then they will expand in a different way. And for the glass sensor, the wire is encased completely in the glass, so there will be additional strain from the glass or from the metal when there are temperature changes. This is not the case in the ceramic sensor. So since the wire can freely move inside the opening, then there is no strain gauge effect. In other words, it does not act like a force sensor as well. But this will be also this will also have an effect on the fragility of the material. So it will not be as good for vibrations and so on. On the other hand, the ceramic PT100s can be used for higher temperature ranges. So ceramic sensors can work for roughly 850 centigrade, but they have to be placed also inside a thermal well for protection. I have here some examples of ceramic thermocouples, ceramic PT100s. So you will see different sizes, but they are all PT100, so they all have 100 ohms. The resistance is the same, the steady state characteristic is the same, but the difference is the size and also the time constant. The smaller sensors will have smaller time constant. The larger sensors, the heat transfer will take longer and they will have a longer time constant. And the last version of a PT sensor that we will discuss will be a thin film sensor. The construction is very different from the two previous sensors. The construction is like this. It's a ceramic substrate, so a ceramic board, and on this we deposit a thin layer of platinum. The material is deposited as a paste. So during the manufacturing process, the manufacturer takes this board, deposits a paste, and then he fires this in an oven, and the paste solidifies and creates a conductive layer made from platinum. The advantage is that this thin film sensor is very small. It uses really a low amount of platinum. So compared to the wire sensors, it will be much less expensive, roughly like 5 times less expensive. On the other hand, this sensor will typically not be good for higher temperatures. So you see up to 600 centigrades. If I would like to measure 800, then I would need to use the ceramic PT100. The size of the sensor can be very different. This is just an example. Here the dimensions are in millimeters. So let's say 10 by 2 millimeters, but it can be also much smaller. I have here some thin film platinum sensors that I will show you. They are here in this small box called PT100. There are 2 of them, and the size here is, let's say, 2 by 5, 2 by maybe 3 or 4 millimeters. So they are very, very small. They will be fast. They will be not that expensive as the other ones, but since they are typically soldered directly on some printed circuit board, the entire application will not be for higher temperatures. Here, to give you an idea about the prices, so roughly 5 times less expensive than the glass and ceramic sensors. The size is small. This could be 3 by 3 millimeters, for example. Thin film platinum sensors are typically used to measure surface temperature. So if you have an object and you need to measure the temperature distribution at the surface of the object, then you can use this thin film sensor. They will also influence in a smaller way the object itself, since the heat conduction will be smaller due to the size. But we will typically not be able to use them for higher temperature ranges. Okay, platinum RTDs are very precise, but also expensive. So you cannot have platinum RTDs in cost-sensitive applications. It would not make too much sense to have a platinum sensor, for example, for air conditioning temperature control. There we also need to measure temperature, but just the sensor itself would cost like 100 euros roughly, and then the temperature controller would be very expensive at the end, so no one would buy that. Also, platinum sensors are very accurate, and there are applications where you don't need this degree of accuracy. You will be satisfied if you measure the temperature within plus minus 1 or 2 centigrades. And you need something that's a lot cheaper than the platinum sensors. So in these applications, we can use nickel RTDs. Nickel is a metal that is much cheaper than platinum, but on the other hand, it is not that stable, and it has a much lower accuracy and linearity. So nickel sensors are good for, let's say, lower precision applications, typically like household controllers that require a low price, but you will be very satisfied if it measures within 1 centigrade. Nickel has a higher temperature coefficient, roughly 2 times higher than platinum, so it will have higher sensitivity. But we will see that there is a problem with this temperature coefficient of resistance, and that it will be non-linear. It will be even worse than, well, much worse than for platinum. Here is to give you an idea how is the equation looking like for a nickel sensor. You don't need to know that. Just keep in mind that it's really a nonlinear equation. You could find those coefficients, but the result is that nickel sensors are used typically in smaller temperature ranges, up to 100 to 120 centigrades. Due to this non-linearity, we are typically not using them in larger temperature ranges. Although the nickel sensor itself could be fine with that, it will be so nonlinear that we will not use this kind of sensor. There are, again, two accuracy classes defined for nickel. If we would compare the values here with the platinum sensor, we will see that the error here is really much bigger than for the platinum sensor, and this sensor is used in, let's say, low accuracy applications. Here is an idea about the steady state characteristic. So the blue line is the PT100 in a range of -50 to 150 centigrades. So we see, okay, really nice linear dependence. The red line, red curve, is the nickel RTD in roughly the same range, so from about -80 to 250 centigrades. Even in this range, we can see just by looking on the chart that it's nonlinear. But if we are somewhere in this range, if we use that for household applications, then it's fine. If this would be, for example, the temperature controller to check the temperature in this room, then we would expect that it will be somewhere between 15 and maybe 30 in the summer. So we'll be somewhere around here, and here we can expect that it will be nice in linear dependence. By the way, the temperature controller is this thing. So this measures temperature in this room, and they adjust the temperature so that we are not cold here in the winter. It does not use the nickel sensor. I looked inside, but it uses an electronic sensor that is similar to this one. The third line in this chart, the black one, is copper. We'll discuss copper in a minute, but you see copper, a really nice linear dependence in large range, but the resistance is roughly 10 times smaller than for platinum or for nickel. The naming conventions for nickel are the same like for platinum. So you see Ni 100, so stands for nickel. 120 is 120 ohms for 0 centigrades. The typical range of a nickel sensor is usually 200 centigrades, up to 200 centigrades, but due to the nonlinearity, we're typically not using it. It can be a wire-wound sensor. It can be also a thin film sensor, which you see, for example, here. So here is an estimate 3 by roughly 3 millimeters is the size of the sensor. Can be smaller, can be bigger. The advantage of nickel sensor is the price. So you see it's roughly 5 times less expensive than a PT100. So it is good for cost-sensitive applications like this thing, the household temperature controller. Here you can see the sensor itself. That's here. Again, the nickel sensor needs to be protected in a thermal well. So it's not installed directly, just the sensor in the application, but it's protected with a thermal well. I don't have any nickel sensor here. We don't use them in our lab, so I can't show it to you. The last RTD that we will discuss very briefly will be copper sensor. Copper is very cheap compared to platinum and nickel. On the other hand, copper is famous for a really bad long-time stability. Have you seen a roof that is made from copper? What happens very soon? It turns green. So that would happen also with your temperature sensor. So copper sensors are good if you want to measure for a short time. So in applications where you just need to check the temperature once, and that you don't care about long-term stability of the sensor. The copper sensor typically is a Cu10, so it has a 10 ohms for 0 centigrades. The reason is the resistivity. The size of the copper sensor will roughly be the same as for a PT100, but since copper has roughly 10 times larger electrical conductivity, then the sensor needs to be smaller. I have here an example of a Cu10 sensor. So that's this one. You see how large that is. And you see it's also very thin. So the typical application of this kind of sensor is to measure, for example, winding temperature in electric machines. So since the sensor is very thin, you can insert that quite easily right into the winding of an electric motor, read the temperature during an experiment, and then you can remove the sensor. So in this kind of application where you measure the temperature of an electric machine, you don't really care about long-term stability. You just want to know, okay, now I have 90 centigrades or 50 centigrades, and if the sensor will not be reading the same temperature in 1 year, then that's not an issue in this kind of application. Copper, you see, has a very nice linear dependence. So it's okay, it's great, it's really linear from -80 to roughly 250 centigrades where we typically use this sensor, but also since we have just 10 ohms, we need a different measurement instruments than for the platinum and nickel sensors. Questions? Okay, and we will conclude today with a third sensor. It will be a thermistor. A thermistor is similar to an RTD in that sense that it also changes the electrical resistance with temperature. So the principle is changes of electrical resistance as a function of temperature. The difference is that RTDs are made from metals, platinum, copper, nickel, but thermistors are made from semiconductors. So it's a piece of semiconductive material, and the changes of electrical resistance are detected, and this acts as a temperature sensor. There are many types of semiconductor materials, and there will be two types of thermistors. One will be NTCs and one will be PTCs. PTC stands for positive temperature coefficient and NTC stands for negative temperature coefficient. Here you have an example of two steady-state characteristics for a PTC and for an NTC. So for an NTC, it's typically an exponential dependence where the resistance is decreasing with increasing temperature. So you also see that it will not have a constant sensitivity, since the slope at this point will be much different from the slope over there. For PTCs, you see that at first the temperature, while the resistance decreases a little bit with increasing temperature, and then it's increasing quite sharply. So the PTCs are typically not used as temperature sensors because you would have to deal with this and with this. PTCs are typically used as temperature fuses. Sometimes it's also called a resettable fuse. So here you have some specific temperature, and when the temperature is above this temperature, you have a quite high electrical resistance. The change here in the electrical resistance can be a few orders of magnitude. So above that, you have a low resistance. Okay, it can be like a wire, and then above a certain temperature, you have higher resistance. NTCs, on the other hand, are used as temperature sensors. So we will discuss only NTCs as temperature sensors. If you see in some application the resettable fuse, then it is a PTC thermistor. As you have already seen on the chart, the resistance of the dependence of resistance on temperature is nonlinear. And we can approximate the dependence by this kind of equation, which is called the Steinhart-Hart equation. And here you have T, that's the temperature, R is the electric resistance, and A, B, C are the coefficients. I just want to show here that the dependence is nonlinear and that this dependence is only an approximation that works in a limited temperature range. If we would express this R from the equation, then you would see that it's an exponential dependence, since here we have natural logarithm. Then if I express R, it will be R equals to some exponential function. You don't need to remember this at all and note that, but I just want to show here the complete function. Here I have resistance, exponential, and there are some coefficients in the equation, and those coefficients A, B, C, and so forth are a function of material. So it's very sensitive to the choice of materials, and even if the manufacturer produces the same thermistor, the same type, if it's a different batch, the properties will be a little bit different. So here, one of the biggest disadvantages of a thermistor will be that it cannot be interchanged in the application without recalibrating. It will also be much less accurate than the metallic RTDs. However, this dependence of resistance on temperature is exponential. Here you have the curve plotted for a thermistor that has 20 kiloohms for 25 centigrades. For RTDs, we had the number valid for 0 centigrade. For thermistors, it's typical that you will see the value for 25 centigrades. And here is the exponential dependence. So here is temperature from roughly minus 40 to 80 centigrades. And you see here the electrical resistance is changing by many orders of magnitude. The 25 centigrades are somewhere around here. And here we have 20 kiloohms. If I would go to, let's say, minus 40, I would have 800 kiloohms. So there is a really large change of electrical resistance. This will have an effect on the circuits that we will use for thermistors and for RTDs. They will be quite different. Since this is changing a lot, we can typically connect a thermistor directly to an ohmmeter and use that as a temperature sensor. So one of the huge advantages of thermistors is that they will not require any expensive equipment to read out the value from the sensor. If we put that in a simplified form, then we see that the resistance depends on some initial resistance. That's the temperature for resistance for 0 centigrades or 25. And it's still an exponential dependence. Here we have the beta coefficients, which you will typically find in a data sheet from the manufacturer. It is dependent on the material, and if you want to use a thermistor in your application, then this typically leads to a sensor that is connected to a microcontroller, and in the memory of the microcontroller you store a table with this dependence between temperature and resistance. So you have a cheap sensor, let's say 10 to 100 times cheaper than an RTD, but on the other hand you have a more expensive electronic circuit because you need a microprocessor, you need a memory, and you need the program that runs inside that. How does a thermistor look like? So it's a small bead of the semiconductor material at the end of 2 wires. I have here some thermistors that I can show you. So those are thermistors. You will see it's always a small bead or some small cylinder of the semiconductor material installed on a 2-wire. This is the thermal well used for thermistors. It's a small tube where you install the thermistor, again for the same reasons like all the other sensors. The diameter of the small ball at the end is typically somewhere in the range of 0.2 to 3 millimeters. The diameter will also have an effect on the time constant of the sensor. The thermistor is a very fast sensor. It's at least 1 order of magnitude faster than a platinum RTD. So if you want really quick measurements, if you want to acquire fast changes of temperature, then use a thermistor. Place that in a small thermal well. But on the other hand, you will need to handle the problems with non-linearity, accuracy, and limited temperature range. I have here some example of industrial and non-industrial thermistors. This is the industrial thermistor. You see the price is roughly $18 US. So this is the sensor, the thermal well, and probably this box as well. So it's very cheap compared to a platinum RTD. On the other hand, it has a really limited temperature range. So thermistors are usually used up to 120, 150 centigrades. For higher temperatures, the semiconductive material degrades. So we can't use thermistors for higher temperatures. So this is a typical range, 150 and nothing more. The typical accuracy is not that bad. You can see plus minus 0.2, plus minus 0.4 centigrades. So it's a relatively accurate sensor. It's very fast, but has a limited temperature range. And of course, it's non-linear. So this is the industrial version. The non-industrial version that you may easily use in your applications if you want to control temperature in a room or in an aquarium and the water somewhere. It's less accurate, but less expensive. So here you see the typical accuracy of a thermistor is something like plus minus 5 or plus minus 10%. So nothing exceptional. We have already seen a thermistor. Do you have in one of the lab tasks? Have you an idea where? It was right on the first lab. Remember, for the first lab, we have the task for uncertainties. And the one of the resistors inside the box was a thermistor. So when we were moving the box, it did pick up the temperature changes, and this acted like the source of inaccuracy or uncertainty in your experiment. So without knowing that, we have already used a thermistor. The typical range is similar to the industrial one, so minus 40 to 120, 150 centigrades. That's the maximum that you can expect. On the other hand, the thermistors that I show you here are really not that expensive, like roughly 8 Czech crowns. So it's a really cheap temperature sensor. Compared to a PT100 where you have 100 euros, then it's nothing. The time constant is very small, so a thermistor is the fastest sensor that you can get. This is an example of time constant for this sensor. It's just the sensor itself, without the thermal well, has a constant of 1.2 seconds. So it can very quickly react to changes in temperature, and you can easily use that to read fast changes. Okay, last thing for today will be how to handle the signals that are coming from the thermistor. We can linearize that in an electric way. It means that we can take this curve, and by using this simple connection, this is the temperature sensor, we use a series and parallel resistor with roughly the same size. We can linearize this characteristic, but only in a small range. So let's say I would like to linearize that for 25 centigrades. I would linearize that in a really small area, and this would give me this type of dependence. It doesn't work in the entire range. If you want to see how that works, then try the online simulation. You can play with the resistor values. You can play with the shape of the characteristic, and you will see that it really works well only in a very limited range of temperatures, let's say plus minus 5, plus minus 10 centigrades. So we can use this in applications where the temperature is not that much changing. Typically, it will have to be done in a different way. The standard way today is to use a microcontroller, so microprocessor that will store this table and will interpolate piecewise this characteristic that is stored in the memory, and then in the output we will have a standard signal like current or voltage or some digital buses. So this is how it's done today. Fortunately, the microcontrollers today are not that much expensive, so but still it will be more expensive than the sensor itself. Although the processors today can cost like 10 Czech crowns, the cheapest ones, you need additional circuits. So if the sensor itself costs 8 Czech crowns, then the CPU and the board make us cost 100. So like 10 times bigger price than for the processor. Okay, we will skip the temperature sensors for semiconductors, and I will just show you some circuits that are good for RTDs and for thermistors. For RTDs, we need to detect small changes of electrical resistance. So the circuit that we will use will be a Wheatstone bridge. We will evaluate the changes of electrical resistance. With that, it will be DC powered, and I will show you two connections with this DC bridge with a temperature sensor. This is the two-wire connection. I encourage you to go later through those schematics. This is the sensor itself. So this is what is changing the temperature, what is reading the temperature. So it's installed somewhere in the thermal well, and there are wires connecting that to the bridge that is somewhere else. This is the bridge itself. We will discuss the connection of the bridge in a more detail in 2 weeks, when we will be dealing with 4 sensors. We'll use exactly the same connection. The point that I want to show you here is that the voltage from the bridge is a function of the resistance that we have here, but it's also influenced by the electrical resistance of the wires that connect that. So if you use this kind of 2-wire connection, then if for some reason the resistance of those wires will change, then you will see a change in the output voltage. The reason why this could change is temperature. So if this would be 50 meters long going through some environment, if you change the temperature, it will change electrical resistance, and you will read that as a change of temperature T here, but it will be in fact the change of temperature of the connecting wires. So this is not a good connection at all. This can be used in applications where you're in a lab and where you have 2 meters of wire and you know that the temperature is not changing. But this is not good for industrial application. In industrial application, we need to compensate for the temperature changes that can occur around the connecting wires. So here, this is a 3-wire connection, still wire resistance, but now we have the wire resistance in this part of the bridge and in this part on the bridge as well. And when in 2 weeks we will write the equation for this bridge, we will see that it will automatically compensate for eventual temperature changes around this wire. So this 3-wire connection is quite useful if you want to eliminate the temperature influence on the connecting wires. You can again try online simulation. I have prepared a schematic and you can play yourself and see what happens when you change the electrical resistance of the wires. The third connection with the bridge that also automatically compensates for the wire resistance is this one. We have, in this case, 4 wires going from the bridge to the sensor. In this case, it's connected just like that, and this is going to the sensor. But again, this is in one part of the bridge, this is in another section of the bridge, and this also compensates automatically for the resistance changes. Here, really, probably before last slide, you can use also this kind of connection, but this is typically used for thermistors. For thermistor, we've seen that the resistance change is much larger than the resistance change of an RTD. So we can evaluate that directly. So this is the temperature sensor, thermistor typically. We supply that with a constant current. So this is a more complicated electronical connection. The current is maintained on a constant value. And we measure the voltage with a gauge, with a voltmeter, which typically has a very high internal resistance. Very high means like 10 mega ohms or higher. And since the current here is 0, almost, due to the high internal resistance, then will not have any influence of the length of the connecting wires, because there will be no voltage drop on the wires themselves. Here you see we have a constant current. We need to supply the sensor also with some maximum current in order to prevent self-heating. So here you have an idea for a PT100 in a bridge connection. The maximum current is typically 1 milliampere. For a thermistor, the current is roughly 50 microampere, so much smaller, because the joule losses given by this equation are a function of current. So if the current is smaller, but the resistance is higher, I need to maintain a good heat dissipation, because otherwise the sensor itself would be a heater and would not be a sensor. Really last slide in the presentation, take a look yourselves at home. It's a comparison of the 3 temperature sensors that we have discussed so far. And I'll post that also on the Moodle. There will be some industrial applications, some industrial examples of sensors, PT100s, where to install that and so forth. Okay? We are at the end.